Hello, I'm Kyle Porter, and today I am presenting generic metadata time carving. And this was a work done by myself alongside my colleagues Rune Nordvik, Fergus Toolan, Stefan Axelsson, and Katrin Franke. So the title is maybe a bit confusing, so let's break it down a bit. So we are not doing traditional file carving. We are carving for file system metadata entries. And the method that we are approaching this in is that the metadata is first carved by looking for evidence of timestamps. So essentially, we are trying to use timestamps as a dynamic signature for finding metadata entries. And the idea is that this approach should be as generic as possible. So we want to be able to apply it to any file system that we come across. But why carve for file system metadata in the first place? Well, this would be in situations where the file system might be damaged beyond any kind of use. So this can be through physical damage, or this could be instances where an image has been reformatted with a different file system. So some advantages of using file system metadata carving is that you can recover files and metadata without using any kind of file system critical data structures. So you don't have to rely upon a MFT file, superblocks, group descriptor tables, etc. Furthermore, you also have a possibility of full file recovery. So you're obviously recovering the file system metadata, and if the metadata entry has essentially a block pointer, extent, data run, etc., to the file, then you can retrieve the file, whether or not it's fragmented or not. Compared to traditional file carving will inherently miss file system metadata, and it has difficulty with fragmentation. So why timestamps as a dynamic signature? Well, we noticed a couple of things. First of which is that file systems typically record multiple timestamps per metadata entry, and that they're typically co-located near each other. And so this table just shows a number of different file systems and the number of timestamps that are closely co-located in their metadata entries. And it's usually 3 or more. Furthermore, we noticed that multiple timestamps within a metadata entry often appear to be equal. This was anecdotal, but you can even look up at some sans posters that show performing certain actions on the system will update multiple timestamps simultaneously. So, but basically, if you have all these features and they are present, and these features are present in most file systems, then we have found a generic feature of file system metadata that we can try to apply to finding metadata entries for any file system. So our research objectives. Can we reliably use time as a generic identifier to carve for file and metadata structures in different file systems? And furthermore, what is the reliability of recovery of files using the discovered metadata in ext4 and NTFS? So does our idea work of time being a generic feature we can search for? And even if it does, is it kind of usable in a practical sense? So this is a kind of bird's eye view of the our entire methodology for generic metadata time carving. You have your disk image, and we apply the generic components of our method, this generic timestamp carver, which then produces a list of potential timestamp locations. And you can try to use this to try to find and identify metadata entries, but it's going to include many, many false positives. And so we have a follow-up program, which is a file system specific parser, which its intention is essentially to filter out all of the false positive metadata entries from this list. And the output from this, this program is essentially a list, a text or Excel file of the discovered metadata for that particular file system. But let's first look at the generic timestamp carving algorithm, the algorithm for finding potential timestamps. And the way we're going to try to understand the algorithm is rather through example. But the main idea of the algorithm is that for each non-overlapping m-length sequence of bytes, so in this case, an 8-length sequence of bytes, we are essentially looking at it as if it were a keyword. And we have a search space in front of the keyword, which we call a search window of length k. In this case, the length is 24. And essentially, you are searching for this keyword inside this search window here. And you're looking for multiple hits of it. So in this rule, we have a rule where you need to find at least 2 matches of the keyword in the search window to say, okay, there is a potential timestamp located at this offset. And you are essentially repeating this search process of this keyword and the subsequent window over the entire disk image. So I'm going to move my face over here so we can see the example a bit better. So in the example, we have the keywords being underlined by this green underline here. We have our search window defined by the brackets. And we have this first test of seeing whether this candidate timestamp is equivalent to this test sequence of bytes over here. We have 1 match. And we check the next non-overlapping sequence of bytes of length m, whether it's equal. And again, it is equal. And so we say, okay, we have found a potential timestamp because this means that there are 3 sequences of bytes of length m, in this case of length 8, that are totally identical. This is a signal this might be a potential timestamp. And if it is a match, like it is here, or if it passes the test, then we advance our search ahead by the length of the search window. And this is so we don't get any overlap or multiple hits for a single metadata entry for its timestamps. Now, if it didn't pass the test, we would just advance the keyword position up by length m, the length of the assumed amount of bytes per timestamp. So this is just a simple string matching algorithm kind of based on this sliding window approach. And it runs in big O quadratic time, more or less, where we have t being represented as an array representing the disk image. And this symbol just means the length of the disk image divided by m, the length of the timestamps, with the floor symbol, of course, and multiplied by k, which is the search window, divided by the length of the timestamps. So as I said before, just running this algorithm and producing a list of potential timestamp locations is likely to produce a lot of false positives. So we need this file system specific parser to use afterwards, which is hand-tailored for a specific file system, which acts as a validator for the found locations of the potential timestamps. And basically what the tools do in general here is it checks offsets from the timestamps for expected features. So the timestamps are kind of used as these anchor points. And you can look at just the expected features you would expect to be offset from the timestamp in the timestamps in the metadata entry. And then we also check features within the metadata entry to ensure it's consistent with itself. So an example for this is for inodes. it has a attribute which shows the length of the file, but then also has an attribute which shows the number of sectors that the file takes up. And we just make sure that these two values are consistent. So onto the experiment. Essentially, the question we were asking ourselves was, can our method extract metadata entries from damaged file systems? And in order to test this, we damaged two synthetic disk images we created, one running NTFS and the other running ext4. And they were damaged by reformatting them with different file systems. So NTFS was reformatted with exFAT, and ext4 was reformatted with NTFS. And just as some additional information, we added into the inodes of this ext4 partition, we added an attribute that contained the actual inode number of the inode itself, because the inode number does not exist inside the actual inode. And this is important for later. So each of the images were 2 gigabytes in size. The NTFS image contained 40 pictorial images of 10 different data types, 4 different data types, 10 files for each, and 10 text files as well. The ext4 image contains 25,000 text files and 50 directories. And of course, each of the images contained system-created files as well. So we recorded the precision of our method's ability to identify inodes or MFT records, because this is essentially the functionality of our tool to extract or identify and extract these metadata entries. And then we also recorded the recall of the known metadata entries that we extracted. So essentially, we were trying to calculate the percentage of files that we could recover that we knew of. In the case for ext4, we focused just on these 25,050 files. And for NTFS, we focused on every single file that we knew about in the actual disk image. So we needed to make some assumptions for our experiments. For NTFS, the only assumption we have to make is we have to assume the length of the timestamp. So this is something you always have to do. So our general method is not entirely general, but you have to make a guess as to what the length of the timestamp will be. So 2, 4, 8, etc. Although right now we only support lengths of 4 and 8. For ext4, we also need to assume some other things. We need to assume the block size. We need to assume that the inodes are of size 256 bytes. And we need to assume the offset to the beginning of the ext4 partition. And the reason why we need to make these additional assumptions for ext4 is that our method, our ext4 file system parser, tries to make guesses of what the inode number and file name pair is for each of the inodes it finds. And this is why we have the inode number attribute inside each inode, so we can compare our guesses to the ground truth. And unfortunately, we don't have time to go over the method and how we made these guesses. Maybe we can take it in the questions. So onto the results. So this is the results for the NTFS reformatted with exFAT experiment. And we obtained about 99.4% precision. We only identified one false positive. And we had 100% recall. So we found all of the files that we knew existed on the disk. So that performed very, very well. The results for ext4 reformatted with NTFS were a bit more complicated. First, we'll talk about precision. So in the first table up here, we see that we actually achieved 100% precision. We found no false positive inode entries. And then for this table down here, this is more or less discussing its recall, but first we're going to focus on this column here. And we didn't write down the percentage of recall, we just recorded the number of files found. And the reason why we did this was because when ext4 was reformatted with NTFS, much of the data was overwritten. A lot of the inodes were overwritten. And so we felt that we're representing recall in terms of percentage. It's a bit confusing because we wanted to show, we couldn't be certain that we missed files due to the fact that there were errors in our method versus we missed files due to the fact that they were simply overwritten. That's why we just have files found. But we found in total 5,755 of the total 25,050 files. And just to explain this rather shortly, each of these rows here, we had a number of ways we could estimate the file name and inode number pairs for each of the inodes. And there are these two different methods here, and the bottom row is essentially ORing the results from both of these methods. So if one of the methods were correct, then we would say, okay, this is the correct, we found a correct attribution of the file name inode number pair to the inode. So in terms of the precision in naming the inodes we found, we achieved a maximum precision of 28.9%. So the results here were much lower for ext4 than they were for NTFS, at least when looking at recall. But let's compare our results to some commercial tools. Could these tools retrieve any metadata entries from our reformatted disk images? And in many cases, we found that no, they could not. And we should emphasize that we were mostly looking for carving the metadata entries with these tools, not just carving the files. So some tools that had some success was EaseUS for finding NTFS metadata entries. I suppose the question mark is here because it's not open source, so we don't know how it works and how it found these entries. The bulk extractor could also obtain the NTFS metadata entries, but these other tools really didn't deal very well with finding the inodes for these text files in the ext4 experiment, whereas our tools could work to some extent. So summary. So this is a quick summary of the analysis based on our results. So for NTFS overwritten with exFAT, a large benefit is that we could find resident files in the MFT entries, which most of the tools missed. Obviously, something like the bulk extractor could read it because it essentially shows a hex dump of the MFT entry. Furthermore, most of the tools had a lot of trouble with the fragmented files. And our generic metadata time carving worked fairly well with it, so long as the metadata entry was not shown as being deleted. So we had some sort of data run or extent or direct block pointer to the data to extract the file. For ext4 overwritten with NTFS, this could possibly explain the rather poor recall. So overwriting ext4 with NTFS more or less wiped approximately 20,257 inodes from the inode table. And we were using, this ext4 partition was using flex groups. So the majority, essentially all of the inodes were in the first block group in more or less a very large inode table. And the majority of these inodes in the inode table were just overwritten. But recall, we recovered 5,755 inodes, which means that we then recovered some 963 overwritten inodes, which we found to be a pretty interesting result. So before was essentially discussing precision and recall, but let's discuss the runtimes for the experiments as well. Running the potential timestamp carving on the NTFS image took approximately 13 seconds. And in running the NTFS specific parser took less than 1 second. On the other hand, for the ext4 image, the potential timestamp carving took about 20 seconds. And I believe essentially as the choice of timestamp gets smaller for the potential timestamp carving algorithm, then it should take more time to scan through an image. And as well, the ext4 parser took about 8 seconds. And this is because the ext4 parser is much more complicated than the NTFS one. We have to do multiples. We have to do at least 2 scans through the disk image where we're doing a lot of operations and trying to make these guesses for the file name and inode number pairs for attributing them to the inodes. So in conclusion, it looks like we can use timestamps as a reliable identifier of file system metadata entries, but we need to filter the results with these file system specific parsers. And we can reliably use our method to fully recover files, so long as the metadata entry contains multiple equivalent timestamps. So if the metadatas have these properties, we should be able to find them. And then lastly, we have shown with the experiments that we can, this can work on images with these damaged file systems. So that is our presentation. Thank you for listening. We have a link to our GitHub with all of the code and the data. You can find that here. And if you have any questions, feel free to ask me or email me or Rune. Thank you.